Hey folks, this is Captain Jones here to talk to you about the von Neumann computer model. This will be our first look at kind of the pieces that come together to make a computer. Our objectives today are twofold. We're going to describe the 5 components of this computer model, so you're familiar with each of those. And then I'll also show you a very similar but slightly different model called the Harvard computer model. And we'll point out some similarities and differences between those two. All right, so let's get started. Excuse me. I feel like we're pretty early in the course at this point. You're familiar with EE360 with digital logic, and you might be thinking, how the heck does this become that? If I get circuits, I get logic gates. I can build a little adder, and how in the world does that somehow form the basis of this thing that's sitting on my desk, this really powerful machine, this computer. So ultimately, answering that question is kind of the goal, a big goal of this course. Today, when we talk about the von Neumann model, we'll get a bit of a high picture view of that. So I want to kind of start this discussion with a graphic based on this pyramid. So we're gonna kind of start to piece together how we can get from our circuits to our computer, and that starts with the things we learned in EE360 and digital logic. The two kind of base layers of this pyramid are our logic gates and our circuits. So, excuse me. So you could think of sort of our computer boils down to, ultimately things like AND gates and OR gates. And forgive this really terrible graphic of an OR gate. But we learned in E360 how these devices work, how they kind of transform binary values, zeros and ones, into other zeros and ones. And over the course of E360, we showed you not just how these devices work, but how we can combine them into other useful devices like a multiplexer or a priority encoder, or even a D flip-flop. You may recall that each of these devices at its heart are just collections of these gates. And at some point we were able to, when we were looking at a multiplexer or a D flip-flop, we could sort of forget for a minute the fact that inside each of those devices was just some type of circuit composed of logic gates. We could abstract, you might say, abstract away the logic gates and treat a D flip-flop as based on the rules of a D flip-flop. And so this pyramid here on the left is sort of it's kind of that. I'm going to refer to it as a pyramid of abstraction because as we move up the pyramid, we're going to take basic components like logic gates and we're going to wrap them up into these things like multiplexers and flip-flops, and we're going to be able to not think of these devices necessarily in terms of the actual logic gates, but in terms of how the components actually function. And what we're going to do in this course then is take components like these, multiplexers and flip-flops and encoders, and then put them into circuits and sort of abstract a way to build into a computer. So the next 2 levels of the pyramid, really you could kind of consider the bulk of this course are going to be in these 2 things that we're going to call the organization and the architecture. And so kind of if I could summarize, the organization is effectively taking these components here, and of course there's some other ones, and combining them to form things like memory, control unit, ALU, arithmetic logic unit, and others. We're going to sort of build these into these kind of more abstracted components that we can then put together to make a computer, to make an architecture. So this is sort of right here, right at this point here, that we have a computer, and the architecture has to deal with sort of the structure of how these components here are connected together in order to make that happen. The last couple levels of this pyramid are predominantly deal with software. You can almost imagine, sort of these top 3 layers as being software, and the bottom 4 as being our hardware. And the idea, when we take this pyramid all the way to the top, is that we have certain problems that we want to solve. We want to be able to send an email to someone, or compute or calculate our tax returns for a given year. And ultimately, what computers do is let us solve those problems. If we were to think of this all the way down to the bottom, it's just we can solve those problems with circuits full of logic gates. And these top three layers are the process of taking those problems that we wanna solve, decomposing them into algorithms. So these are sort of structured ways to solve problems, decomposing those into some type of programming language that's able to implement that algorithm. And once we have this in a programming language, we can actually run that on our computer, on the architecture that we have in front of us to potentially do something useful. Okay, so let's take a look at one such architecture. So this is where we're kind of right here in the pyramid. One such architecture called the von Neumann model. And the von Neumann model has 5 components you might remember from EE360. The first being memory, which is where we store our data and our instructions. And you can see here in this graphic that the component that is memory includes very two important things called MAR, MDR, which stands for our memory address register and our memory data register. And the way this works is that the memory unit is a pretty simple device. You give it an address, it spits out a piece of data. And so to kind of communicate with that, we're going to put sort of a memory address register on the front end and a data register behind it. And when we load the memory address register with the address of a piece of data, then depending on whether we're reading or writing, the data register will either store that piece of data into the memory or return that piece of data to somewhere else in the computer. Our second component is the processing unit. We might have referred to this in EE360 as our data path. And so you can see here I've got 2 arrows that sort of move information or move data back and forth from memory to the processing unit. And you could probably make the argument that it's the movement of data from memory to the processing unit and back to memory that by and large constitutes the functioning of our computer. So the processing unit has, you can see here, kind of 2 major components. One is the ALU, which is our arithmetic logic unit. So that's the device that does the actual kind of number crunching, so to speak. It might add, or it might subtract, or it might perform a logical or a logical and, or something like that. And then typically in the processing unit, we also have some kind of temporary storage. So this is just a little placeholder that allows us to store some temporary values while we're doing maybe longer or larger calculations that doesn't necessitate us kind of moving stuff to and from memory. While we're doing our calculations. All right, the computer's got to be able to sort of talk to the outside world. So we've got our third and fourth components of the von Neumann model are the inputs to our computer and the outputs that it produces. So you can see some examples here of inputs and outputs to our computer, and at least in the case of our disk, right, our hard disk or a thumb drive, it's potentially both. There's lots of things that could potentially fall into both categories, and this is how we as humans interact with the computer. You'll notice that the inputs and outputs in this diagram are or they're talking directly to memory. So the inputs sending stuff to memory, memory sending stuff to the output. This is a term we'll look at in Unit 3 called memory mapped I/O. So in effect, even talking to our inputs and our outputs effectively involves the processing unit just sort of talking to memory. Memory provides a facade, if you will, for us to interact with the inputs and outputs. And then, of course, lastly, we've got our control unit. So this is the orchestrator, this is the conductor, this is the thing that tells all the other 4 components what to do. And you can see here that all throughout this diagram, there's little dashed lines, little tendrils from the control unit that go to each of the other components and control them in such a way as to do something useful, to make a computer. Our control unit has itself 2 really critical components. One is down here, PC, which stands for program counter. I think it's supposed to be in the shape of a finger, which is probably to indicate the fact that the PC, the program counter, is marker of where in our program we are currently sort of executing which instruction we're executing. So, like a finger kind of points to the spot in memory where we're executing an instruction, and each time an instruction is finished, that little finger, that pointer, moves to the next instruction in the sequence. And then IR on the right here stands for instruction register. So this is a register that holds the value of the current instruction that's being executed, and it will keep that value there, kind of unchanged until it's completed its execution, at which point it sort of gets loaded with the next value in the sequence. All right, so these are our 5 components to our von Neumann model: memory, processing unit, input and output, and the control unit. Okay, let's talk about the difference between the von Neumann and the Harvard architecture. You can see the 2 diagrams here taken from our sort of supplementary textbook, Basic Computer Architecture. And you probably notice right off the bat they're very similar. Really the biggest difference is that in the von Neumann architecture, we have a singular structure for our memory, which contains not just our program, our instructions, but also our data. And in the Harvard architecture, we have separate memories, one for instruction and one for data. And that's the biggest difference between the 2. There's some advantages and disadvantages to either one, which I encourage you to look into. But the purpose here is just to kind of show you that the von Neumann architecture is a very important thing to understand. It's very ubiquitous in computing, but it's not the only architecture. There's an example one here, and in fact, I think in the should do exercises, there's a couple other architectures that you're encouraged to read about, and there's lots more. But this is just to kind of give you a perspective of what's one alternative architecture for our computers. Okay, so today we talked about the von Neumann architecture. We started to kind of build the big picture for our class, and so the von Neumann architecture sat at this level in our pyramid of abstraction, and we use this to sort of frame how we're talking about our computers. I mentioned how EE360 kind of by and large dealt with these 2 lower layers of the pyramid, our logic gates and our circuits, and we were able to use those to build things like D flip-flops and multiplexers and even finite state machines. Over the course of this course, we'll focus very heavily on these 2, and really, and to a little bit extent, this one right here, these 3 layers of the pyramid. The organization has to do with how those circuits come together to make things like our memory, our processing unit, and the von Neumann architecture is one example of how those larger units connect together to make our computer. We saw 2 sample examples of an architecture, not just the von Neumann, but the Harvard architecture, which have this subtle difference where in the Harvard architecture, the instructions and data reside in separate places in memory. And that was useful to kind of see that there are just other architectures out there. All right, folks, I'll leave you with our quote, which is brought to you from Steve McQueen, who said, "When I believe in something, I fight like hell for it." I'll see you next time.